Hello, we are back again talking some more about acids and bases, and specifically we're going to be looking at a calculation that is called pH, and we're going to be looking at how that pH is an indicator of how acidic or how alkaline a solution is. Okay, so pH here is related to the concentration of hydronium ions, and if you remember, hydronium ion is H3O plus, and it is formed by the proton or the H plus from an acid combining with water in that aqueous solution. Okay? We're going to look at how pH is calculated, and the property of pH. Basically, you can use it. You can measure it using a probe, or you can use pH paper, pH strips. But we're also going to look at the actual calculation of that, so you understand how that is calculated and what you actually are calculating, what you're measuring. Okay. You may already know that when you have a pH of 7, that means that the solution is neutral, and above 7 means it is acidic, and below 7 below 7 it is acidic, and above 7 it is basic. Okay, so we have a scale here, a pH scale, that basically goes from 1 up to 14, and 7 being in the middle. Here, if you've got a low pH actually means it is more acidic. A high pH means it is more basic. All right, but I may be getting a little ahead of ourselves, so let's jump into Model 1 and look at what we have here. These are ion concentrations for acids and bases. So in beaker 1 through 10, we have different solutions that are given to us. Notice we are given the concentration as well as the formula of the particular compound that is dissolved in water, aqueous. And we are told whether it is acidic, neutral, or basic. Then we are told over here the concentrations. If you have a formula put in brackets, that means concentration. Concentration, meaning molarity. Molarity, if you remember, is the measurement of moles per liter, or in short, you could just say a molar. Okay? And then this calculation over here, we're going to take the concentration of the hydronium ions and the concentration of hydroxide, and we're going to multiply them together. Okay? All right. What does the symbol of bracket, open bracket, H3O plus, close bracket in Model 1 indicate? It is the concentration of the hydronium ion. Okay? In beaker 2, which ion has a higher concentration, hydronium or hydroxide? In beaker 2, we come up here and we see that when we're looking at the concentrations, in scientific notation, if you've got negative power, that actually is a small number. The more negative this power is, the smaller it is. So this is 1 times 10 to the negative 3, or 1 divided by 10 3 times. This is 1 divided by 10 11 times. So if you remember scientific notation, this means we'd move this decimal point over to the left 3 places. That's 0.001. Whereas this value here would be 0.0, 10 zeros, and then a 1. Okay? So here you have the hydronium is higher in that case. Describe how the concentration of hydronium ion was calculated for beaker 3 in Model 1 from the concentration of the acid. So if we look up here in beaker 3, let's compare concentration of the acid and concentration of the hydronium. Well, isn't that interesting? They're exactly the same number. This is 0.00001, which is exactly 1 times 10 to the negative 5 in scientific notation. These are the same value. because every HCl unit is going to release one H plus into the aqueous solution, which is going to create your hydronium. So every mole of HCl is going to create a mole of hydronium ions, or every 10 to the negative 5 moles is going to create 10 to the negative 5 moles of hydronium. Okay? Same value. It's just that one is written in standard form and the other is written in scientific form. Describe how the concentration of hydroxide ion was calculated for beaker 8. This time we're looking at beaker 8. Beaker 8, same thing here. Notice that we've got 0.0001, and that is 1 times 10 to the negative 4. This is for hydroxide now, hydroxide. So it says beaker 8 hydroxide ion. And for every unit of NaOH, we're going to release 1 hydroxide ion into the aqueous solution. So however concentrated this particular compound is in the aqueous solution, that is going to be your concentration of hydroxide ions as well. Okay? Now, I will mention that some acids have 2 H's in them. Okay, so in that case, if they're going to release both H's into the aqueous solution, your hydronium concentration would be double the concentration of your acid. Or some bases, like calcium hydroxide, has 2 hydroxides for every 1 unit of the base. Okay, which ion, hydronium or hydroxide, has a higher concentration in an acidic solution? And then down here, notice it says which ion, hydronium or hydroxide, is more concentrated in a neutral. So let's just look at concentrations and compare when we are determining if something is acidic, neutral, or basic. Well, if it is acidic, which is the case for the first 4 here, we're comparing these 2 concentrations, hydronium and hydroxide. Remember, if these are negative values, the more negative your power of 10 is, the smaller it's going to be if that numerical value is the same. So this is 10 to the negative 1. This is 10 to the negative 13. 10 to the negative 3, 10 to the negative 11, 10 to the negative 5, 10 to the negative 9, 10 to the negative 6, 10 to the negative 8. So these values here, since their negative power is a little bit bigger than these negative powers, your concentration of hydronium is bigger in acids. You have a greater concentration of hydronium ion when you have an acidic solution. I'm going to maybe jump ahead here a little bit, but you may be realizing that for a basic solution, then the concentration of your hydronium is going to be less than the concentration of hydroxide. The concentration of hydroxide is going to be greater than the hydronium when you have basic solutions. And when it's neutral, well, you guessed it, the concentrations are going to be the same. Which statement is true for basic solutions? The hydroxide ion concentration must be less than this, 10 to the negative 7. The hydroxide ion concentration must be more than 10 to the negative 7. Or the hydroxide ion concentration must be more than or equal to that. Well, for it to be basic, you don't want it to be equal to 10 to the negative 7 because that would mean it is neutral. And you don't want it to be less than that because then that means the hydronium has to be greater and you would have acidic. So you want your concentration to be more than 10 to the negative 7 for hydroxide in order to make a basic solution. Let's look back up here just to confirm. For all your basic solutions, these values, all these numbers right here, are greater than 10 to the negative 7. So we have this following statement. Acidic solutions contain hydronium ions. That's true. while basic solutions contain hydroxide ions. Okay, that's true. Is the student's statement correct based on information in Model 1? It's true, but you have to realize that acidic solutions contain hydronium ions. That's true, but they also do contain hydroxide ions to a lesser degree. And basic solutions contain hydroxide ions. That's true, but they also contain hydronium ions. It's just that the quantity is less. So it is a comparison. Which do you have more of? If you have more hydronium ions, if the concentration of hydronium ions is greater than hydroxide, then it's acidic. If your concentration of hydroxide is greater than the hydronium, then it's basic. Calculate the quantity, concentration of hydronium times the concentration of hydroxide for each of the 10 beakers in Model 1. And if you've got people to help you, you can share the load. Well, I'm just going to tell you really quickly here that if I take these pairs of numbers and I multiply them together, I'm going to get, in every single case, I'm going to get 10 to the negative 14, or 1 times 10 to the negative 14. 10 to the negative 14, 10 to the negative 14, okay? 10 to the negative 5 times 10 to the negative 9, when you multiply powers, you add the exponents. So in every single case here, I'm going to get 10 to the negative 14 all the way down there. If you know the hydronium ion concentration, how could you determine the hydroxide ion concentration? Well, we just calculated that their product in an aqueous solution is always 10 to the negative 14. So if this product of the two concentrations in an aqueous solution is always going to be equal to 10 to the negative 14, then if you know the one, you could take 10 to the negative 14 divided by the other to find the missing concentration. Okay? So the hydroxide would always be 10 to the negative 14 divided by the hydronium. And the hydronium would always be 10 to the negative 14 divided by hydroxide. Okay? A solution has a hydroxide ion concentration of 10 to the negative 3. What is a hydronium ion concentration in the solution? So all we have to do to find the concentration of hydronium is I take my product. I know these two concentrations in an aqueous solution always have to equal 10 to the negative 14. I'm going to take my 10 to the negative 14 and I'm going to divide by my 10 to the negative 3 here. And I know that that's going to give me 10 to the negative 11. So my concentration of the hydronium is 10 to the negative 11, which is basically 0.0, 10 zeros, and then a 1. Okay? That's molar, by the way. That's molarity. It's really small. Is the solution acidic, neutral, or basic? How do you know? Well, if the concentration of hydronium is equal to 10 to the negative 7, then I know that it's neutral, because hydronium and hydroxide would both be 10 to the negative 7. But if the hydronium is 10 to the negative 11 and the hydroxide is 10 to the negative 3, well, hydroxide is greater than 10 to the negative 7, so it must be a higher concentration than the hydronium. Hydroxide is a higher concentration than the hydronium. If hydroxide is greater in concentration than hydronium, then you're going to have a basic solution. Okay? So this is basic. A solution has a hydroxide ion concentration of 4.79 times 10 to the negative 3. What is the hydronium ion concentration of the solution? Again, hydronium. You're going to take your hydronium ion concentration to find this. You're going to take 10 to the negative 14 and divide by 4.79 times 10 to the negative 3 on your calculator. And whatever number that is your concentration of hydronium. Okay? Is a solution acidic, basic, or neutral, or basic? Well, I know that this number right here, that number is greater than 10 to the negative 7. So I've got more hydroxide ions than I do hydronium ions in this aqueous solution. So I know that this is going to be basic. I know that the concentration of hydroxide is greater than the concentration of hydronium. Okay? Let's read this together. It says the value, 1 times 10 to the negative 14, or just 10 to the negative 14, is the equilibrium constant for the autoionization of water. We mentioned this before in a previous video, that in water, water is always going to a very small degree, self-ionize, meaning a water molecule is going to react with another water molecule, and one of the water molecules is going to donate its proton, its H plus to the other one, creating hydronium ion and hydroxide ion. There they are, both of them. And if I take the concentration of these two ions, hydronium and hydroxide, and I multiply them together, I am going to get 10 to the negative 14. It should be an equal sign here. Okay? Kw, that is the equilibrium constant for water. W is 10 to the negative 14. Remember how we express this? The K value is always products. It's the multiplication of the concentration of the products at equilibrium over the reactants. But we do not include liquids, pure liquids or solids in this K expression. So over here the reactants are just water. So we don't have any reactants that we would include. And we're just going to have the concentration of the products, which are what? Hydronium and hydroxide. So the K expression is going to be this right here. For water, the K expression for the autoionization of water is a concentration of hydronium times the concentration of hydroxide, and it is always going to equal 10 to the negative 14 at a particular temperature. If you change the temperature, then it's going to be different. But at standard temperature here, this is basically, I think this might be at 25 degrees Celsius. I'm not sure about that. But at a particular temperature, this is what your Kw value is. Okay? If you change the temperature, that K value is going to change, but it's always, doesn't matter what temperature it is, it's always the hydronium times the hydroxide is going to give you this K value. Okay? For the autoionization of water. This equilibrium occurs in all aqueous solutions. It doesn't matter if now you add something to pure water. If you add something to pure water, these two concentrations may change, but their product is always going to be 10 to the negative 14. So if you add something to water, like if you add HCl to water, the concentration of one of them may go up, but that means the concentration of the other's got to go down to keep the product of the two equal to 10 to the negative 14. Or if I add something like NaOH, well, this may cause the hydroxide to go up, and that means that the hydronium's got to go down in order to keep this product equal to 10 to the negative 14. Always, 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 it's going to be 10 to the negative 14 at a particular temperature. So the result of this equilibrium are as follows. All aqueous solutions have some detectable concentration of both hydronium and hydroxide. And the product of these ion concentrations is always 10 to the negative 14, and that is called the Kw, the equilibrium constant for water. Now, we're going to be using logarithms here in this particular video, because if you notice, we've been working a lot with powers of 10. 10 to the negative 3, 10 to the negative 1, 10 to the negative 14. Well, log just means exponent. That's all it means. Log means exponent. So we need to just review how we use logarithms in this course, because we need to use them when we're talking about powers of 10. So we're going to use this pattern here to kind of remind us how we find the log of something. So the log of 1, this is in base 10 by the way, the log of 1 is 0, the log of 10 is 1, the log of 100 is 2, the log of 1,000 is 3, the log of 10,000 is 4. Why is that? So what are we finding when we do log? The log is equal to the exponent. That's all you have to remember. So when I say 10 to what power is going to give me 100, I'm asking you the log of 100 is what? That's another way to say it. The log of 100 is what? So I'm asking you 10, this is all in base 10. I don't need to write it, but sometimes you'll see the base 10 down here. 10 to what power equals 100? Okay? So if I say the log of 1, I'm asking you the exponent. What is the exponent? 10 to what power is going to give me 1? Well, that would be 0. 10 to the 0 power equals 1. 10 to what power is going to give me 10? That would be 1. 10 to what power is going to give me 100? That would be 2. 10 to what power is going to give me 1,000? That would be 3. 10 to what power is going to give me 10 to the 4? 10 to the 4, there it is right there. Okay? Here, this is asking the same question. 10 to what power is going to give me 0.1, which is 1/10, or as an exponent, that is 10 to the negative 1. So 10 to what power gives me 0.1 or 1/10 or 10 to the negative 1? Negative 1. This is 1 over 100, or 10 to the negative 2. So 10 to what power gives me 0.01? Negative 2. 10 to the what power gives me 1 over 1,000 or 10 to the negative 3? Negative 3. So if you write this in scientific notation, it's really kind of helpful, especially if it is 1 times something, 10 to some power. This power right here is going to give you, that's what you're looking for. 10 to what power? That's what you're asking. So when you take the log, you're asking, give me the exponent that I would raise 10 to in order to get this number. Okay? All right. 13 then. Let's look here. Use the examples in Model 2 to explain how logarithms are calculated in terms of factors of 10. So every time the log, you are asking, find the exponent that you have to raise 10 to in order to get a certain number. Okay? So 10 to what power gives me some number. The log is going to give you that power, that exponent. What would be the logarithm of 1 million? Well, 1 million. So there's a million. That is 10 to the 6th power. So if I take the log of that, I'm asking 10 to what power gives me a million? Or 10 to what power gives me 10 to the 6th? So the log of 1 million is 6. Alright, you're going to need your calculator here, and hopefully you are familiar with it in order to use powers of 10 and logarithm. So make sure you become familiar with your scientific calculator if you haven't already. It says here enter at least 3 of the examples shown in Model 2 into your calculator to verify that you know how to find the logarithm of a number. So you can enter in, take the log of 1 on your calculator. You're going to get 0. Take the log of 100. You're going to get 2. You can take the log of any number if you want to. Alright? And show that you're going to get something that maybe you'll be able to approximate it and kind of estimate what it would be, and verify that you're actually getting these numbers here on your calculator. Okay? So use your calculator to find the logarithm of 250. If you take the log, log, if it's not written, remember this is base 10, the log of 250 This is asking the question, by the way, 10 to what power equals 250? Now, you may not know exactly, but we do know that 10 squared is 100, and 10 cubed is 1,000. So 250 is in between 100 and 1,000. It's closer to 100. So it's probably going to be 2.2, 2.1 something, 2.2 maybe. It's closer to 100 than it is to 1,000. So you could even estimate just by comparing it between 10 squared and 10 cubed. You know that it's going to be 10 to something, 2 point something there. Okay? But ask your calculator, and you should be able to see what your actual answer is. All right? Oh, and we just said this right here. So this is saying exactly what I just said. You should be able to find out that it's going to be between, your answer is going to be between 2 and 3. Okay? First, estimate the answer for each of the following. Then find the answer using your calculator to check your estimate. Okay? So in this one here, if you do this, I'm just going to give you the answers really quickly here. So if you do the log of 7,800, this is going to be between 3 and 4, because 7,800 is between 1,000 and 10,000. Powers of 10. The actual answer here is 3.89. The log of 0.045 is negative 1.35. And the log of 3.4 times 10 to the 9 is 9.53. And the log of 7.2 times 10 to the negative 4 is negative 3.14. Okay? So do notice here, these values that are greater than 1 are going to have positive log values. If they're less than 1, you're going to have negative log values. All right, now let's see how this applies to pH, because pH actually, you need to know logs in order to calculate the pH. Here we have Model 3, and Model 3 is giving us concentration of hydronium, and it's given us in two forms, the decimal notation, scientific notation. These two values are equal. Those two values are equal. All right, they're just written in different forms. And then it's taking the log of that concentration, and then it is showing us the actual pH. And we're going to use this model to discover, oh, how is pH actually calculated? Columns 1 and 2 in Model 3 both give the molar concentration of hydronium ion in solution. What is the difference in the way the first two columns express? So this first column right here is expressed in decimal notation, or sometimes just called standard notation. Okay, so it's decimal versus scientific. And scientific is going to have a numerical portion multiplied by a power of 10. This numerical portion has to be between 1 and 10, by the way. It's going to be 1 point something, 2 point something, etc., or 9 up to 9 point something. Okay, so that would be the correct form, and then power times some power of 10. Fill in the missing values in column 1 and 2. So 1 times 10 to the negative 3, that would be 0.001. And then this one, 0.0001, this would be 1.0 times 10 to the negative 4 molar. Okay? Estimate the missing logarithms for solutions B and E in Model 3, then verify the answers using the calculator. Okay, so this is log of 5.5 times 10 to the negative 3. So we know our answer here, if we were to estimate it, it's going to be negative 2 something between negative 2 and negative 3. So this is actually going to be negative 2.3. Okay? And down here, we've got negative 4.6. And we know it's going to be between 4 and 5 because it is close to 10 to the negative 5 there. It's a little bit bigger than 10 to the negative 5. So once you take the log of these numbers We have them here. You'll notice how we get pH is then we get rid of the negative value. So this pH is going to be 2.3, this is going to be 4.6, and we're going to see that play out here as we continue these questions. All right. Using the examples given in Model 3, write a sentence or mathematical equation that describes how to calculate pH from the hydronium ion concentration. So pH, let's look at the process that we went through here. We took the concentration of hydronium ions. Doesn't matter which form you use. You can use decimal or scientific, doesn't matter. But you take the log of that concentration, you're going to get a value, but it'd be nice if that value wasn't negative, so we take the opposite of that in order to get the pH. So pH is the opposite, or the negative log, of the concentration of the hydronium ions. That's how you find the pH of a solution. All right? Now I'm just going to point something out to you here. Look here. You see that, do you realize that these concentrations up here at the top, that 1 times 10 to the negative 2 is actually a larger number than 2.7 times 10 to the negative 5. This negative 5, that's a really small number. That's 0.00027. 1 times 10 to the negative 2 is 0.01. This number is bigger than this number down here. But look at the pH. The pH value is smaller than this pH down here. Small pH tells me larger concentration of hydronium ions, because when you take the log of it, you're going to get negative 2 here, whereas you get something like negative 4 down here. Yes, the log of this value is smaller than this one, okay? And you take the opposite of it, so the pH value is going to be smaller. Okay, this log down here is smaller than the negative 2, but now you take the opposite of it, you got to have a 2, which is smaller than 4. So it gets confusing. What you need to realize is a small pH means a larger concentration of hydronium ion. Small pH, large concentration of hydronium. The smaller the pH, the larger the concentration of hydronium ions. Okay? So we did this, we did the pH values. Calculate the pH of a solution that has hydronium ion concentration of this. So all you have to do on your calculator is you take the negative log of this number, 10 to the negative 8. Now it's easy if it's just power of 10, like 1 times the power of 10, because I take the log of 10 to the negative 8, which is asking what exponent do I have to raise 10 to get 10 to the negative 8? Well, that's negative 8. And then I take the opposite of that. So this answer right here, this pH is just 8. Okay, this here, this is 7 times 10, 1, 2, 3, negative 3. This is a little bit more difficult, but you can use your calculator. This is pH is equal to the negative log of 7 times 10 to the negative 3. This is going to be like 6 point something, okay? So in this case, I'm sorry, not 6 point something, I'm looking at the 7, I mean, that's going to be 2 point something, okay, this negative 3 right there. So in this case, we get the log of 7.10 to the negative 3 is negative 2 something, 2.2 I think, and then you take the opposite of that, so you get a positive 2.2. Okay? That's your pH here. If we want to compare these two, this pH is smaller than this one. So 2.2 is smaller than 8, obviously, and that's because this concentration is larger than the 10 to the negative 8. So this is more acidic. A low pH means it's more acidic than a higher pH. In fact, this pH is over 7, so this would tell me it's more basic. Okay, this is a basic solution. Find the hydronium ion concentration in a solution if you were given the pH. This time we're going to go the other direction. So if pH is equal to the negative log of the concentration of the hydronium ions, Do you know what the inverse operation of log is? Well, remember I told you that log is just an exponent? So the inverse operation of log, that log operation, is 10 to a power. You're taking 10 to a certain power. So if you have pH is equal to the negative log of the concentration of hydronium ions, and you want to find the hydronium ion concentration knowing the pH, the hydronium ion concentration is equal to 10 to the negative pH value. Okay? So for example, if you know the pH, and you know the pH is 6, then your concentration of the hydronium ion concentration is going to be 10 to the negative 6, negative pH. And here, hydronium ion concentration here is going to be 10 to the negative 5.43. And you can just ask your calculator if you want to. If you want to express it as a number in decimal notation, just take your calculator, take 10 to the negative 5.43, and it'll give you a decimal equivalent of that. Why does neutral water have a pH of 7? Well, when water is neutral, that means that the hydronium ion concentration and the hydroxide ion concentration are equal, and if their product is 10 to the negative 10 to the negative 14 in water at a certain temperature, then they both have to have a concentration of 10 to the negative 7 when it's neutral. Okay? Because the square root of 10 to the negative 14 would be 10 to the negative 7. That means that gives you a pH. If the hydronium ion concentration is 10 to the negative 7, that means you get a pH of 7. The negative log of 10 to the negative 7 would be 7. Which solution has a greater hydronium ion concentration? One that has a pH of 4 or one that has a pH of 8? Low pH meaning, what does that mean? If the pH is less than 7, it is acidic and has a relatively higher concentration of hydronium. Okay? Or another way to say it is that the concentration of the hydronium is greater than the concentration of the hydroxide. If the pH is less than 7. If the pH is equal to 7, that means the two concentrations are the same. And if the concentration of the hydroxide is greater than hydronium, that means that pH is greater than 7 because, as mentioned, the hydronium is less than the hydroxide. Okay? So this would be neutral, and this would be basic. A solution with a pH of 1 is twice as concentrated in hydronium ions as a solution with a pH of 2. Explain why this statement is not correct and write a sentence that describes the correct relationship. Well, you have to remember pH is not just a factor here that you're multiplying by. It is a logarithmic operation. It's a logarithmic function. It's not a linear function. So the solution here, if you have a pH of 1, that means you have a concentration of hydronium ions equal to what? 10 to the negative 1, which is 0.1. Okay? If the pH is 2, that means the concentration of hydronium ions is 10 to the negative 2. That value is 0.01. Well, that's not double. If you take 0.1 and you multiply by 2, you get 0.2. No. If you have a pH of 2, it means actually that it is a factor of 10. So a solution that has a pH of 1, actually the concentration of hydronium ions is 10 times greater than the pH that a solution that has a pH of 2. Okay? So 0.01 times 10 would give you the 0.1. Okay? Not 0.01 times 2. So this 0.1, a pH of 1, is actually 10 times greater than a solution that has a pH of 2. All right. Let's look at our extension questions here. Our extension questions are looking at Model 4, and we're looking at pH and pOH. pOH, where did that come from? Well, pOH, we can also find the negative log of the concentration of hydroxide. If pH is the negative log of the concentration of hydronium ions, then guess what? pOH is the negative log of the concentration of hydroxide ions. Okay? You can think of P just stand for power, like log. Log, remember, is just an exponent, just the power. Okay? So let's look at the examples in Model 4. If you know the concentration of hydroxide ions in a solution, how can you determine pOH? So as I just mentioned here, and it's walking you through this, we can take the negative log of the concentration of hydroxide to get the pOH, as mentioned right here. Okay? Consider the data in Model 4. Calculate pH and pOH for solutions A, B, and C. So we're adding these two. So A, B, and C, we're adding 3 and 11, 14. 9 and 5, 14. 2.28 and 11.72, 14. Isn't that interesting? So we know that the pH and the pOH, they're always going to add up to, in an aqueous solution here, at a particular temperature, always going to add up to 14. Okay? So if you know one, you know the other. If you know the pOH, you would just take 14 minus that pOH in order to get the pH. Fill in all the missing values from Model 4, and if we do that, we have here, given one of these, and this is interesting, all you have to do is be given one of these and we should be able to find the other three. If I know pOH, I know that pH and pOH have to add up to 14. So this has to be 10.32. And if I want to find the hydroxide ion concentration, I just take the pOH and I can take 10 to the negative 3.68. Okay? And if I know the pH to find the hydronium, I can just take 10 to the negative 10.32. Okay? Or I could have, once I know the concentration of hydroxide, I could have taken 10 to the negative 14 and divided by the concentration of hydroxide to find the hydronium. So you can see that if you just have one of these, I can find all of the other four. 9.28, I can find pOH because I know that pOH and pH have to add up to 14. So this has to be, what, 4.72. Okay? And then I would just take 10 to the negative 4.72, 10 to the negative 9.28, and you can fill in the rest of these. And these are always going to add up to 14, 14. All right? If you're given the concentration, then I could take 10 to the negative 14 and divide by this concentration, 3.02 times 10 to the negative 3, and that's going to give me my concentration of hydronium. And then I would just take the negative log of that concentration to get my pH, and then I could take 14 minus the pH to get my pOH. Okay? So here's a little something that you want to be able to be very good at. Okay? I'm just going to write a little table here for you. Let's say that we have the concentration of hydroxide, we've got concentration of hydronium, we've got pOH, and we've got pH. Those are your four values that are often used when we're talking about acids and bases: concentration and pOH and pH. You should be able to go around all four of these if you're given even just one. If you're given one of these, you should be able to find the other three. Let's just look and see how we do that. Remember, if we go between pOH and pH, all we have to know is that they add up to 14. So if you know one, you know the other, because they add up to 14. So if you know pOH, you would take 14 minus pOH in order to get pH. If you know pH, how do you go to pOH? 14 minus pOH. They have to add up to 14. Let's go this direction. If you know one concentration, you should be able to find another concentration. If you know either of these concentrations, they multiply. Their product is 10 to the negative 14. So if you know the concentration of hydroxide, you would take 10 to the negative 14, divide by that concentration, and you would have hydronium. And if you know hydronium, you would divide by 10 to the negative 14 divided by that hydronium concentration, and you'd have hydroxide. Now let's go between these. If you know the concentration of hydroxide, how do you find pOH? Negative log of that concentration. And how do you go the other direction? 10 to the negative pOH gives you the concentration. Likewise over here, if you know the concentration, you take the negative log of that concentration to get your pH. And if you know pH, then you take 10 to the negative pH to find your concentration. Okay? So in question number 30 here says calculate the concentration and pOH of a solution that has a concentration of hydronium ions given there. So you could use this table right here to come up with your answer. All right? And as you do so, if you want to refer to this table, that's fine. I'm going to let you know what the answer is, and then you can check to see if you get it correct or not. Okay? In number 30, your concentration of the hydronium ion is 10 to the negative 4. Your concentration of the hydroxide is 10 to the negative 10. Your pH is 4, and your pOH is 10. Okay? I think that would be quite obvious just by looking at the value there. Okay? All right, I hope that is helpful, and this kind of wraps up our short unit on acids and bases. We've talked a lot about acids and bases. We defined them, then we looked at whether they're strong acids or weak acids, and now we concluded by looking at pH, pOH, and the concentration levels to determine whether a solution is acid or a base. All right, great job. We will see you in the next video.